Good evening. For this programme, we're going to talk about the material that makes up the universe. But before that, do you remember our Moor Winter Marathon? We asked you to look at and describe the most interesting objects you can see in the night sky. Now to find out what we can see this month. Pete and Paul.
Pete and I have come to Wirksworth in Derbyshire in the Peak District to see this lovely work of art called a star disk. It has all the constellations which make up the sky and a perfect location to talk about our Moor Winter Marathon. 50 objects for you to see in the winter night sky, and many of you have already started. Here are some of the images which you've posted on our Flickr site. Mick Hyde's Kemble's Cascade is at number 17, is lovely. So too is number 8, the star cluster in Auriga taken by Paul Hutchinson. This wide shot has lots of objects, number 7, 8, 9 and 10 on our list. You just need your Mark 1 eyeball for many of the objects. To help you find them, try using a Planisphere.
So this month we're going to look at some of the naked eye objects you can see with the Moor Winter Marathon. And I brought a fantastically simple tool with me to help me locate these objects.
A Planisphere, I've got one of these. These are great. These are really good if you're learning your way around the sky for the first time. And it's basically, well, it's the star disk that we have here with a piece of plastic on top showing the night sky that's available.
That's exactly right. I mean, all the stars, you shouldn't really keep pulling it apart like this, but all the stars you can see underneath represent all the stars you can see in the sky throughout the entire year.
Yeah.
Now, of course, you can't see that in one go. So what happens is that there's an overlay printed on the top with a window in it. And that window represents just the stars you can see at a specific date and time of the year. So all we have to do is put that window in the correct position for your current date and time. So, for example, if we wanted to observe the sky at 10 p.m. in the middle of November, let's rotate that round so that the time, which is 10 p.m, which is there, lines up with the middle of November. Now, those stars in that window that we can see there represent the stars we could see in the sky at 10 p.m.
We also have some other interesting things on here. We have the western horizon, the eastern horizon, and the north and south. Those are quite useful for orientating the thing, aren't they?
Absolutely, because if we wanted, let's start with the south. We've got the southern horizon here. If you hold it up so that the southern bit is at the bottom, then that part of the sky you can see there would be what you'd see to the south. But they are incredibly simple and they don't cost very much either, just a few pounds. And it's a great way of finding out what's in your particular night sky at any time of the year.
Agreed.
So now let's go on to the Moor Winter Marathon.
Yeah, so we're going to start over here, aren't we? Actually, I'm very near to where we're going to start with the Hyades and the Pleiades.
Those are the first two items on the Moor Winter Marathon. And of course, we've also at the moment got a wandering object down there, which is Jupiter. And it's not shown on the star disk because it moves about over time.
It's a wandering star.
It's a wandering star.
If we should move over now to the constellation of Cassiopeia. These are Cassiopeia, very, very distinctive constellation.
A W in the night sky, yeah.
And around about here, it's the double cluster.
Yeah, which you can see as a sort of misty patch with your eyes, but really the best view is with a pair of binoculars.
It is,
it is. Stunning.
It's that wonderful sort of tornado of stars spilling out into space. It's quite wonderful.
Nice description.
Do you like that? It's mine.
Let's go back now to an object. Well, it's not an object.
No.
It's a pattern.
It's your made-up asterism.
It's an unofficial pattern.
OK, yeah. I'll show it out. I'll walk it out on the star disk.
OK, this is the celestial G, and this is what's known as an asterism, an unofficial pattern of stars in the night sky. So to start out, you're going to have to go to Aldebaran.
Oh, right, OK. So
you've got a bit of a walk ahead of you here.
OK, off we go.
So now head up to Capella, which is in Auriga.
OK, here we go. The yellow star.
OK, and now down to Castor and Pollux, the two bright stars in Gemini, the twins.
There we go.
Now down to Procyon, which is the brightest star in Canis Minor, the little dog. Down to Sirius, the brightest star in the night sky. And then Rigel, up to Bellatrix, and then across to Betelgeuse.
It's most of the sky.
It is most of the sky, but it's a really fun pattern in the sky, especially for kids, to point out some of the brighter stars that you can see.
It is. Let's hope we get some cold, clear nights in November for you to take part in our Moor Winter Marathon. You can find the lists, guides and information on our website, bbc.co.uk/Sky at Night. Next month, we will talk about some of the things you can see with a pair of binoculars. A whole world of clusters and even a galaxy. Now it's over to Chris Lintott, who's on Selsey Beach on the trail of dark matter. It's the story of stuff and what makes up our universe.
Everything's the same here on Earth. Whether it's the sea, the air, the rocks, they're all made of atoms. Whether it's hydrogen, oxygen, nitrogen, or any of the rest, it's all the same. But that's not true of the universe. Wherever we look in the universe, rather frustratingly, something just doesn't quite add up. In the cosmic sweet jar, the coloured jelly beans represent the stuff that makes up you and me, which makes up the planets, the stars, and even the galaxies. The rest, amounting to 6 times as much, is made of something we don't see, a mysterious substance known as dark matter. In our cosmic sweet jar, the result is more black jelly beans than anyone could possibly devour. But in space, the consequences are rather more serious. Dark matter is responsible for shaping everything that we see. What's so shocking is that there's so much dark matter, and yet it eludes direct detection. We can see its effects, we just can't hold it up for inspection.
So, Carlos, I think we've got some jelly beans to help us illustrate dark matter.
Carlos Frenk and Chris North are joining me in the search for dark matter.
We must make sure, though, that people realize that the dark matter is not made of jelly beans.
Well, even with jelly beans, it seems like a strange idea that we don't know what most of the universe is made of. But it's not a new idea, is it?
It is not a new idea, but it is certainly the case that dark matter is one of the most profound mysteries in the whole of science today. Now, the story goes back to the 1930s, when astronomers realized that galaxies are not just uniformly distributed around the cosmos, but they like to collect in entities that are well defined. The most visible of those are galaxy clusters.
These big cities of galaxies with hundreds of galaxies.
Hundreds or thousands of bright galaxies, all making a galaxy cluster.
So how does a cluster tell you about dark matter?
Well, galaxies in the clusters are swarming around, and astronomers asked a very simple question. What keeps a galaxy cluster together? Must be the force of gravity. What else? And then came the real shock, because when astronomers worked out how much gravity the galaxies that we could see produced, they realized there was a gravity deficit, that there had to be 10 times more mass in the cluster than the mass that they could see in the form of stars. It was recognized that something else that is not stars, it's not gas, is something else, hopefully not jelly beans, something else, was responsible for keeping galaxy clusters together. And those news was a real stunner. The universe is full of stuff we cannot see.
And so that was the 1930s, and this endured as a mystery. And then I guess the next shock came when people looked not at clusters of galaxies, but at galaxies themselves, individual galaxies like our own Milky Way.
Exactly, and the story was exactly the same. In a galaxy, in a beautiful galaxy, these amazing things that nature has made.
Just like the sun goes around the centre of the Milky Way.
Exactly. Why does the Milky Way not just fly apart?
And the answer is gravity again.
And not the gravity of what we can see, because that's only a very small fraction of the gravity that's needed. And it is dark matter that keeps our galaxy in place. Okay. Thank God for dark matter. Otherwise, our galaxy would not exist.
And where's the dark matter?
Well, the dark matter is very much not in the disk. It's in a much larger volume. It's in what we call a halo. It's a spherical region, roughly, around the galaxy. And quite a lot larger than the stars are as well. It's normally a few times bigger, and you get this halo of dark matter.
And it's the gravity from the halo that keeps the disk stable and enables it to be able to turn.
And the other source of evidence for the existence of dark matter comes from the phenomenon of gravitational lensing. Now, imagine Chris is a background galaxy.
Yeah, you're doing
and
very
imagine he looks like one. He looks
for the dark
galactic. And here is a galaxy cluster.
Yep, with some dark matter and some ordinary matter.
And some ordinary matter. And Chris is a source of light. A light ray from Chris coming towards me, I'm the observer, will be bent by the concentration of mass. Bending of the light will cause Chris to become blurred and distorted
In a characteristic way,
in
right?
a characteristic way.
We'll
Not
see.
characteristic of me.
No,
you say.
but we'll see you as an arc. And if you look at galaxy clusters, you see these arcs, don't you, around the outside of the cluster.
And if you get it exactly lined up, you get a full ring. It's called an Einstein ring.
Now, how does this tell us about dark matter?
Well, I was about to ask.
Well, you can look at a galaxy cluster and the way it bends light, and you soon conclude, if you can do your sums correctly, that the amount of mass in the visible part of the galaxy is nowhere near enough. The next important question, what is the dark matter?
Well, one way to solve that mystery is to try and make some dark matter. We can see the effects of dark matter in space, but for the last quarter of a century, astronomers have been trying to find it here on Earth. They bury their detectors deep underground, and just a few years ago, the Sky at Night descended into Bolby Salt Mine in Yorkshire to see what a dark matter detector would look like.
Here I am in a lift going 3/4 of a mile underground in Bolby Mine toward this strange observatory.
Despite all this effort, dark matter is still elusive, and so instead of waiting for a direct hit down in a mine, some scientists have grown impatient, and they're trying to produce their own dark matter at the world's most famous laboratory, CERN. We think of objects like this rock as being pretty solid, but it's not. It's full of billions of separate atoms. Each one has a nucleus with protons and neutrons surrounded by a cloud of electrons. Inside each proton is a whole world of even smaller particles, whose effects become apparent when protons are smashed together. In Geneva is the world's largest machine, the Large Hadron Collider, or LHC. It's probably the most sophisticated experiment ever carried out, and it's certainly impressive. Here, protons are accelerated to close to the speed of light, and then smashed together so that physicists can pick over the debris.
It's weird that the very small stuff that we look at actually influenced how the whole of the very big scale stuff in the universe.
Astronomy
actually.
and particle physics together. John Butterworth was part of the team that used the LHC to find the infamous Higgs boson particle, the one that gives everything mass. In looking for the Higgs, they had to recreate the conditions that existed in the early universe, just after the Big Bang. John, how's the early universe different from the one we have today?
It's about symmetries, and the best way to explain it is with a wine bottle.
Good, I like
So-
wine bottles, that's excellent.
So I look down the bottom of that.
Okay.
It's symmetric, right? All around
It's
the middle
round,
of the
right?
bottle.
So you can't, any direction's the same at
That's
the end
right.
of the bottle,
Now,
right?
put something in it.
Well, I've got one of Carlos's jelly beans, luckily, so let's drop that in.
That'll
Okay.
do. Now, if you look down the end, it's not symmetric
No, the
anymore.
bean's at the bottom.
The bean has broken the symmetry.
Okay.
Yeah.
Yeah, no, that makes sense. So that's no longer symmetric.
Right, so the early universe was very symmetric, and the reason is there was a lot of energy, so the bean was jigging around.
Okay.
There's an equally likely chance that it'll be anywhere around the sides of the bottle.
That's right, it might be on the left or the
Completely
right.
symmetric around the middle.
Okay, and so we're back to a symmetric universe.
That's right. But as you cool down past where the energies of
As
the
the
LHC
universe
are,
expands, as everything cools down, if you don't have a collider, the beam drops to the bottom.
that's right, this is everyday life. The bean is off on one side, the symmetry's broken. And it's only by having the symmetry there, the symmetry's still there in the bottle. We haven't changed
yeah, we haven't
physics.
changed the universal physics.
That's right, it's just the cold bit when the bean is no longer got loads of energy, then the symmetry's broken. And that symmetry breaking there is actually how mass occurs in the universe. The only way we can have the symmetry we need in the theory at high energies, but have mass in everyday life, which is clearly there,
Yes.
is to have basically a bean in a wine bottle. Is to have a symmetry that's broken, that's broken by the thing slowing down, but is there again if you give it lots of energy.
And that idea of symmetries is so fundamental to
Yeah.
physics. And there we are with a wine bottle and a bean.
That's right.
Fabulous. Whenever the particles collide, all the debris should fly off in a roughly symmetrical fashion. If that doesn't happen, then that might be the signature of dark matter. The sign we're looking for might be there already, buried in the data that the LHC has already provided. Now, you found your Higgs, so particle physicists are happy, although you've got other stuff to look for. For us, as astronomers, what we need you to do is find dark matter. Is there any hope of the LHC helping us out?
There is indeed hope. I mean, you may be surprised to hear that actually, because dark matter is, of course, dark. It's hard to see. But there is a chance that the LHC is actually a dark matter factory, that we're actually making dark matter in the
Right
lab
now?
right now, yes. It will be hard to see. In fact, the particles themselves we will not see. But we surround the beam with these huge detectors, which are essentially concentric layers of different technologies to interrogate these collisions. So if we see something flying off in one direction and nothing in the other direction, then we know something's missing. We know the event is imbalanced and we know something must have been there.
Because the rules of physics say that roughly things have to go in equal directions.
Yeah, the momentum is conserved.
And so that would look like in your detector, if you've got your collision here, you'd have stuff going in this direction, and if you see nothing, you know you're missing something.
Yeah, exactly.
Okay, so any sign of dark matter yet?
No.
And that's expected, right? It's going to take a while.
Well, no, there were a lot of theorists who thought we might have found it by now and would have told us experimentalists that we would have done, but we haven't yet. The thing is, the whole business of the LHC is that we're looking in this completely new regime of physics, where these forces unify, where the Higgs lives in the wild.
Which, as you said, is the point.
That's right. And so there's a very good chance that if dark matter is some new fundamental particle, this is the region where it lives. And there's still plenty of space to look. We started looking, and we've kind of landed on the shore of a new country of physics. OK, the dark matter wasn't hanging around on the beach, but it might be further inland. And we're exploring that now, and we've got a lot of exploring to do still.
We're still only in the very early stages of its voyage of exploration, but nature doesn't give up its dark secrets easily or quickly. In the meantime, astronomers can still see the evidence for dark matter. The most powerful telescopes in the world stared at this collection of galaxies, and by watching how light is bent as it passes, we can build this computer simulation of the dark matter, showing the galaxies embedded in a wider cosmic web. We don't have computer simulations, but we do still have our jelly beans. So dark matter's great fun, this great mystery, this unknown of the universe, but why does it matter? Why do we care about dark matter, Carlos?
Why does dark matter matter? Well, it matters a lot. In a sentence, without dark matter, we would not be here. Nothing of what we know in the universe would exist without dark matter. Because dark matter is the architect of the universe. It's the agent that has enabled the universe to create all these amazing galaxies and stars that we see around it. Without dark matter, the universe would be completely boring. It would be totally uniform, amorphous, there would be nothing. Let me show you how this works.
Okay, sure. Because we start off with a very smooth universe.
The universe was very smooth. It had only very tiny, small irregularities. Here's a smooth universe.
Okay, full of dark matter.
Nothing, full of dark matter in the proportion of 1 to 6.
Okay.
All mixed up, and all without any structure, without any shape, without anything interesting. But then, inexorably, gravity